Hello, welcome to SPMM Revision on Demand. In this podcast, I will discuss some of the important graphs used when reporting a meta-analysis. There are four major graphs that are important for your exams. Of these, we have already examined a forest plot in detail in the previous podcast. I will now take you through the other three: funnel plot, Galbraith plot, and Labbé plot. Firstly, the funnel plot. To draw a funnel plot, you need two sets of values. On the x-axis, you plot the standardized effect estimate. Example, effect size Cohen's d, or odds ratio, or relative risk, either directly or after a logarithmic transform. In the y-axis, you plot a measure of precision, generally the inverse of standard error or the actual sample size values. Sometimes researchers draw an inverted funnel plot. In this case, you need an inverse measure of precision on the y-axis. Funnel plots can be used for all types of meta-analysis. They are useful as visual aids for detecting publication bias and to assess heterogeneity. This picture is a funnel plot. A vertical line representing the pooled summary effect size is shown here. You can see that large studies produce results that are close to the pooled summary effect, which is likely to be the true value. But large studies are usually few in number. Small studies produce results that are scattered widely around the pooled summary effect. We will see a symmetric funnel that shows increasing scatter with decreasing precision if there is a complete collection of unbiased studies. In this case, a triangle centered on the summary estimate and extending two standard errors on either side will include about 95% of studies. What causes asymmetry in a funnel plot? If there is a publication bias, because smaller studies without statistically significant effects remain unpublished, this will lead to an asymmetrical appearance of the funnel plot. Asymmetry can also arise due to heterogeneity. For example, if all small studies report large effect sizes favoring the intervention, the funnel will be asymmetrical. Next, let us discuss Labbé plot. To draw a Labbé plot, you need two sets of values. On the x-axis, you plot the proportion responding to placebo, that is, the control event rate from the individual trials. On the y-axis, you plot the proportion responding to active treatment, that is, the experimental event rate from the individual trials. Labbé plots are used for meta-analysis that report on binary outcomes. They are particularly useful when combining randomized controlled trials. Labbé plots help investigate the potential sources of heterogeneity in a meta-analysis. For example, we can identify studies that have an unusually high placebo response rates. This may help to identify clinically heterogeneous trials. In the next slide, we will see what inferences can be made from a Labbé plot. In this Labbé plot, the control event rate, CER, is on x-axis. EER, the experimental event rate, is on y-axis. Circles represent individual trials. The size of circles represents sample size of the trials. You can display subgroups of studies with varying colors if you wish. Trials with better treatment effect will be in the upper left half. Trials with better placebo effect will be in the lower right half. Line of no effect Studies falling on this line will have comparable EER and CER. In other words, studies falling on this line will have a relative risk value close to 1. A meta-analysis looking at interventions for smoking cessation reported that nursing intervention is no better than control interventions. A Labbé plot of this meta-analysis reveals that a number of studies report very high quit rates, greater than 40%, without any intervention. This is very atypical of what happens in the real world for smokers. A closer look revealed that these studies were all conducted in general hospital setting, coded in dark blue. Your motivation to quit smoking may be very high after a cardiac or a thromboembolic event for which you are admitted in a general hospital. Studies in primary care setting, shown in light blue, typically report a lower CER and a lower EER. Here is an exercise to recap our skills when reading a Labbé plot. Identify the study with the largest sample size. The study with the largest circle is the study with the largest sample size. Identify the study with the highest placebo response rate. This study would be on the lower right half, and you can see on the x-axis the CER value, and the circle pointed out here has the largest CER value. Identify the study where RR is highly likely to be 1. In other words, the study where EER is very likely to be close to CER. The study pointed out here lies on the line of no effect. This is a study which is highly likely to have EER and CER values equal to each other. Okay, now moving on to Galbraith plot. This is also called radial plot. To draw a Galbraith plot, you need two sets of values. On the x-axis, you plot a measure of precision. On the y-axis, you plot the standardized effect size. In this sense, a Galbraith plot is nothing but a funnel plot with x and y-axis interchanged. Galbraith plots can be used for all types of meta-analysis. They are often seen as alternatives to forest plots. A Galbraith plot provides a better visual display than a forest plot when there is a large number of studies. In this plot, you can see that the x-axis displays a measure of precision, which is 1 by standard error, and y-axis shows the effect P, standardized using the standard error SE. Dots or points represent individual trials. In this particular example, there are no dots, but the names of the trials, the names of the countries from which the trials originated, have been indicated. Studies further away from the origin have greater weights and contribute more to the summary estimate. Imprecise estimates of effect lie near the origin. A regression line with slope equal to the summary estimate is drawn in a Galbraith plot. Two lines are drawn at a vertical distance of plus or minus 2 above and below the regression line to represent 95% confidence intervals around the estimate. Studies outside of these limits are outliers that contribute to the heterogeneity. Sometimes a horizontal line of no effect passing through either a 0 or 1 is also drawn, similar to a forest plot. Here is an exercise to recap our skills when reading a Galbraith plot. Identify the study with the most imprecise result. Study number 9 is closest to the origin. This is the study which is most likely to be imprecise. Identify the study with the largest effect. Study number 7 has a large effect size, nearly 4. Identify the study that is an outlier, though very precise. There are 3 outliers, study number 1, number 9, and number 11. Of these, The most precise one is study number 1. This is pointed out in this picture. Now it's time to ask yourself a few questions. Thank you for choosing SPMM course for your revision.